In this video, I will be talking about how to do the calibration on POWGEN. So to do that, either you can go to the web browser and then go to analysis.sns.gov and then launch a session from there to log into the analysis cluster. That's one way. The other way is using ThinLink, like what I'm doing now, to use ThinLink to connect to the analysis cluster again. And once you are in there, you can launch the terminal by clicking on the icon down below. And then on the terminal, if you are not familiar with the Linux command, cd is representing for changing directory. And then we can give it a directory name /sns pg3 shared calibration. And then you can list out all the contents in the directory by executing ls space -al, and you can see the contents there. The other way to go into the directory is for sure to use in the file browser. So again, the same location, shared calibration, and then you can see the contents in the folder. And then if you want to go to the terminal from within the file browser, you can go to any blank spot and right click to bring up the context menu, and then you can click on the open terminal here. You can see the same thing. So we are located in this directory on terminal. You can list out the contents without problems. And once you are in the directory on the terminal, for doing the calibration, there are maybe two things to do. The first thing is to write contents into the configuration file to control how the calibration will be done. So to do that, on terminal you can use the vim command to open this file. And if you do prefer the GUI way to do that, you can go back to the file browser, to the directory, and then open this same file, cal_config.json. Double click, you can just use any text editor you want to edit the file without problems. So here for the demonstration purpose, I will be staying on the terminal using vim, because that's the thing that I'm comfortable with. So the first entry on the top is the most critical, which is the diamond run we want to use for doing the calibration. And here it has to be the full path to the Nexus file corresponding to the diamond run. But if you don't know the full path, say you only know the run number, you can copy the run number, come out of the editor, go back to the terminal, and execute this command called fend data. You give it the instrument name and paste in the diamond run number, and then it will tell you the full path to the diamond run file. If you go back to the JSON file, that's something we can paste into this first entry in the JSON file. The next one is the run cycle, so it's probably not going to be used for the calibration process. It's only for our information purpose, but anyhow, it will be beneficial to get this right anyhow. The instrument name, date, and the sample environment is the information that will finally go into the file name of the generated calibration file, the .h5 file. So this one, those information are necessarily to be right. And note is something we can put down as a very short and brief note, and that note sometimes, if you need, it can go into the finally generated H5 file, as well. But if you don't, you can just leave it blank. Output directory is the location where the finally generated H5 file will be saved into. So again, it's something that we want to make sure to be correct. So the PD calibration entry is the parameters actually controlling the behavior of the calibration. So normally we can just use them as a default value as shown here. But if you do want to check out the details for the meaning, for example, the parameters, you can check out this website or documentation page for the Mentate, because the Mentate algorithm PD calibration is the bottom level algorithm that is used for doing the calibration. So all the documentation, the information can be found here in this documentation page. The final line is the menu mask. So sometimes the PD calibration is probably missing some bad pixels, and if beforehand, before we do the PD calibration, we already know the number of the index of those bad pixels, which can be saved into the XML format. If you know that, if we already have the file, we can definitely use that and put it here to combine with whatever mask that will be generated using the PD calibration algorithm. So, and then later on, the mask generated by the PD calibration will be combined with the manual mask that we manually put here. So the directory here is relevant relative to the current directory where this file is sitting, basically this calibration folder. So if you check out the contents of the file, the menu mask is pointing to the 2022, the cycle, blah blah. And then if we do a ls-al and paste in the file name, we can see it is sitting there. So that means it is in the folder here. And for the subfolder is masks, and the file name is this guy. So once we have all the information ready in the JSON file, we can then execute the calibration using the command sitting here, the pg3_cal. To do that, on the terminal in the same spot, we can do // representing the current directory, the command name, pg3_cal. So that's the only thing that we want to execute to process the calibration. So what we'll do, it will just read in the information that we put in the JSON file, do everything, do the calibration, and save the file into the output directory that we specified in the JSON file. So that's the only thing we want to do. And here I'll probably just want to skip the execution of the command because it will take some time. But anyhow, after putting in this command like this, you can just press enter to execute it. Let's just cancel it, and that's one of the ways to do the calibration. Actually, this is just a manual way of doing the calibration, and in practice, we do have the automatic way to do that. Actually, we don't need to do anything if things are just working normally, and it should just work normally. And by that, what I mean is that once the diamond data is collected, once the data file, the Nexus file is ready, because the auto reduction engine has already been configured in such a way that once the data file is ready, it will just automatically kick off the auto reduction. And specifically for the diamond run, the auto reduction script is written in such a way that once it detects a diamond run based on the sample composition and the counting time and a few like indicators telling the auto reduction engine this is the diamond run that we want to do the calibration ways. And then in that case, things just happen automatically. So this JSON file will be populated with contents automatically, and then the auto reduction routine will kick off the calibration automatically. And then after some time, maybe several tens of minutes, 10 or 20 minutes, something like that, the calibration file will be ready in the directory that is written into the JSON file. So if things are working normally through the auto reduction routine, it will be always saved into this output directory. So if we copy this file path and then go back to the terminal and say want to list out the contents of this auto-reduce folder, and you can see all the past calibration file that was generated by the auto-reduction routine. So we have talked about using exactly the same routine actually, but one way is to do it manually. The other way is just rely on the auto-reduction to do its job properly. In most cases, it will be doing the job properly without problems. So that's the first way actually to do the calibration. There is another way which is even more manual. If you prefer, you can go to the managed workbench, and to do that, actually we have a local version which we can guarantee it is working properly, because with the managed upgrade sometimes it will potentially break our routine, so that's possible. If we do want to make sure that we want to use a managed version that we ourselves are sure to be working properly, so that's the thing we can use here. Again, on the terminal, the same location, /snes/pg3 shared calibration. In the folder we have this file, managed workbench. And again, on terminal, if we are located in this directory, we can do /, again representing the current directory, and give it the executable file name, then press enter. So give it several seconds. So the local version, for some reason, is a little bit slow, but it's okay. So as you can see here, the GUI is already showing up. And then once the local version is ready, you can see it's using the 6.8.0 version. That's one of the early versions. Now the the production version is 6.9.0 as I'm making this video. But this one is the early version that we have made sure it is working robustly. And close that welcome window. We can go to the file, open script, and we can find the calibration script that we want to use for doing the calibration. So that's the full path you can see on the top to the script, and here is the script we want to use for doing the calibration, and we say open. And here is the contents of the calibration process. So all the codes that it will be executed for doing the calibration. So here for the demonstration purpose, I already have previously running, because as I said, running the calibration will take some time. So this one is one instance that I was running previously for this demonstration purpose. And you can see that all the workspaces have already been generated. But anyhow, if you have never run this script before, you just launch the managed workbench. As we just showed, you can load in this script and hit this execution button to execute this script to run through the calibration routine. But to do that, the only thing that we need to start with is to change this workspace name that we are highlighting. That's basically telling the program which daemon run we want to use. And if you do want to change the parameters, you can go into the codes and change the parameters for the PD calibration. But we don't want to do it here. If we want, definitely we can. So sometimes the managed workbench may not be find this daemon run file. So that's possible, possibly because the configuration of the machine. If that's the case, saying that once you run this script, it will probably just complain something about the file not being found. If you do have that situation, you can go back to the terminal. So you can just open a fresh new terminal, like opening the tab, like what I'm doing now, or you can go to the bottom to click on the terminal again to launch another window of the terminal. Anyhow, we go to the terminal, execute find data PG3, and give it the daemon run number as we already did before. So here is the full path to the file, and we can go back to the managed workbench and paste in this file name echo entry. something like this, a double quote, and paste in the full path to the file name, and that's it. So that's just the only will be used if the original way of doing it like this is not working. If it is not working, just put in the full file name, and that's the only thing we need to worry about. And then after that, let's just click on this run button. It will just run through the script until it's done. Excuse me. So it will take maybe 10 or 20 minutes to go through the process. So once it's done, all the necessary workspaces that we will be using next will be showing up on the left hand side. And then the thing next is to load in the menu mask, because as I said, sometimes some masks may not be caught by the PD calibration. So we want to put in the menu mask manually. So to do that, let's just load mask. So this is the algorithm we want to use to load the mask. And we put in the PD3 as the instrument name, and give it the full path to the input menu mask file. And then give it a name, say this is the menu mask. You can give it whatever name you want. This is the output workspace to store the input menu mask. And then hit run. And the menu mask is now generated. The next thing is to combine the mask generated by the PD calibration and the menu mask. So this one I'm highlighting now is the mask generated by the PD calibration routine. And to combine this mask with the menu mask we just imported, we can go to this algorithm input box, say binary operate masks. And then we put in the input workspace 1, which can be the mask generated by the PD calibration routine. And the 2 is the menu mask. And then we can give it a name like what I'm showing here, the combined mask. Again, this can be arbitrary. So after that, you can see the combined mask is appearing in the tree. So then we have everything actually that we need to save into the calibration file, the H5 file. So go to the algorithm input box again to tap in save diffcal. So that's the that's the algorithm we want to use to save the calibration file. And we want to have the calibration workspaces which contains the DFC values for doing the calibration. And in this case, it should be the PD calib. And the grouping workspace is the grouping workspace telling the program in the later on data reduction stage how to group the detectors. And again, it will be generated automatically by the PD calibration routine. For POWGEN, normally we just group all the detectors on the instrument into one single spectrum. And then we give it the mask. So in this case, we want to select the combined mask. And finally, we just want to give it a file name. And we can use the browser to browse into some locations. Say, for example, this one. This is just, I'm randomly testing. So anyhow, you can give it a name. Because it's done manually, you can give it whatever name you want by putting in the name here. So, but anyhow, having that, you can just hit the run button, which I'm going to skip for the moment. But that's probably just all the ways you can use to generate a mask on POWGEN. So, thank you.